Alright, this is page 131. The definite integral as a number. That's a definite integral as a number, right? This is a definite integral as a function, okay? So this is a function that's accumulating. This is accumulating, all right? And what we're going to do now is look at the second fundamental theorem of calculus. All right, in some other textbooks, they just call it the fundamental theorem of calculus part 2. Okay, doesn't matter what you call it. There's 2 parts to the fundamental theorem of calculus, and this is the second one. So why do they call it the fundamental theorem of calculus? Well, this is like the unifying idea, right? So now with this, we have the integral and differentiation all wrapped up, right? So this is saying taking the derivative of an integral and they undo each other, right? So integration and differentiation is not quite like square root and x squared, right? Square root and x squared, they cancel each other out. But this idea, they cancel each other out. It's not the same thing. It's not an algebraic operation. So this is a calculus thing. I don't even want to call it an operation, right? So we take the derivative of an integral and you get the inside pop out. Now, the biggest difference is you're going to take this variable and replace the t with it. Okay, so we're going to replace the t with x when we take the derivative. So it's with respect to x, you're taking the derivative, right? So whatever's up here, that's got to be the variable. Those two got to be related. But the inside here is going to be a different variable, okay? If you notice up here, this is the chain rule. Okay, this is the chain rule. So we're taking the derivative of u with respect to x. So that's what that means. So you're going to substitute the u into t. So you're going to replace every instance of t with whatever is up here, and then take the derivative of whatever is up here. All right? All right, so let's look at some examples. So the derivative of this integral is just x squared plus 1. Right? When it's a simple x up here, you just replace the variable with that variable with x, and that's it. That's the answer. This is the answer to example A. That's it. All I did was rewrite this with x instead. Example B. Again. Oh, and some of you may ask, well, what about the number down here? It doesn't matter. That number doesn't matter. So this is 2. That number doesn't matter. So it's just 5x minus 3. And you're done. That's it. Okay, so this is the first time I don't have a plain old x up there. I have a complicated thing. All right, so now we're going to substitute that into there. That's going to be 5x squared plus 1. And then you have to take the derivative, which you just substituted, which is 10x. I guess you could clean that up, but let's not. Let's just leave it like that. All right, so that's the answer to C. Let's look at D. Okay. D is not friendly. D is not friendly. So D, I'm going to just copy on a separate sheet of paper because that's going to take, there's not enough space for that. So it's d dx of 2x cubed to x of 3t plus 1 dt. Alright, there's not enough space for that. Alright. Because what you're going to do is take this, you're going to spread this out. You're going to spread this out. Because our theorem, our fundamental theorem of calculus, has to have a constant down there. This is not a constant. This is another variable. Alright, so what we're going to do is split this up. So first thing we're going to do is take this and split it up. This is going to be equal to x to 0 of 3t plus 1 dt. I have to zoom out so I have enough space for this. Pause while it focuses. Alright. Plus 0 to 2x cubed 3t plus 1 dt. Alright. And by the way, we're going to call this f of x. I'm calling this whole thing f of x. And what we want at the end is f prime of x. So we're going to take the derivative. Okay? Alright. But here's the thing. Our theorem, though, has the constant at the bottom, not at the top. So even this is not good. So what I'm going to do is flip it around. So that's going to be the opposite of 0 to x of 3t plus 1 dt. The other part is okay. I forgot. What was it? 2x? Is that a cube? I need stronger glasses, maybe. All right. Okay. Now we're going to take the derivative. Sorry. Now we're going to differentiate. So take the derivative of that. Okay. So that means that negative is there. And I'm going to replace the t with x. So that's 3x plus 1. Okay. And then here, we're going to replace this t with 2x cubed. Times the derivative of 2x cubed, which is 6x squared. So that's the derivative of f. Okay. Let's clean. Well, do we want to clean this up? Not really. Let's leave it like that. All right. If you want to clean it up, that's just algebra. If you want me to clean it up in class, I can clean it up, but I don't care. All right. Oh, now she mentions a net change theorem. Right? I've already talked about this. Right? So the net change theorem we mentioned earlier, they also have other words for it. They call it displacement. So if you're given a rate and how much you displacement. So displacement is different from total distance travel. So displacement is kind of like if you start at point A here, okay, let's say you're on a horizontal line, okay, and this function describes distance that moves like this, and then you go backwards, and then you go forwards, right? So displacement would be how far are A and B apart. Well, total distance travel would be how far is that, how far is that, how far is that, and add all three together. So that would be the total distance travel. And that's displacement. Displacement is how far have you moved from A to B. While total distance travel is what's the actual distance covered. So you go from here to here, then go back. So this area is actually counted 3 times in my example. Okay. All right. So let's look at that. Yeah, we'll just go continue. All right. Oh, maybe not. Maybe I'll edit that video.